For 20 years, cameras circling in space have made the whole Earth familiar. That blue globe carries the feeling of home, even though humanity does not appear in the image. Orbit's only 500 miles high, and the photo shows a view closer to the maps. Here, the moon of Italy thrusts into the sea. This daytime scene is still lonely. The forms of land are here, but none of life. In a nighttime scan from orbit, our own presence is at once conspicuous. It is city lights that dispel the global darkness. Those photographs are novelties of our time. They were all made by machines in orbit. From that high vantage point, the lens can catch a big scene of Earth, a substantial portion of the great globe. But that was not the first time that we understood in detail the form of the Earth in which we dwell. Here I have big books, full, not of photographs of the Earth forms, but of maps. There is Florida with all its bays and inlets and capes. Across the face of Europe, the cities are located in their right positions. And the boot of Italy thrusting familiarly into the Mediterranean. They are not new. This book, 50 years old. This book, 100 years old. But they had no orbiting machines. They hardly had aircraft flights. The occasional mountain might give them a distant view. Yet they mapped the world as a whole, completely, accurately, handsomely. How could they do it? That is the story I want to pursue. Not only for itself, but as well because it is a kind of parable for the growth of understanding in many branches of science far from the work of the geographers and the navigators. On this green Virginia hilltop, Thomas Jefferson, surveyor and architect, built his estate years before he became president. We came to map his wonderful home, Monticello, using the simplest of means. A convenient position marked on the wide lawn. Paper, ruler, and pen. And a line of sight, as straight as light can travel. The terraces and the corners of the famous house are what we sight from the first position. Archaeologist Fred Wiseman is our surveyor, and Phyllis Morrison his assistant. We plotted our sight lines ending at the little house where Jefferson lived while his great house was going up.
Okay, that's it, the last one.
That's the last point from this position.
Yes.
Our map requires more than just one point of view, so we move. We draw as we go, using the portable desktop.
Okay, I guess we're ready to level it.
Position 2.
I think this leg has to come up.
Much tilt would certainly distort the sight lines. Gravity lets us level our plane table at every location. That gravitational guarantee runs through all kinds of mapping.
Just right.
Beautiful.
Then we sight the very same points again from the new position. The ruler crosses the earlier sight line, and that intersection fixes a point on the little house. We drew a line from a corner of that house to our mapping position.
Okay. Now, third line.
Well, that's the beginning of our map of Monticello. The three strong lines describe the house, correct in shape and drawn to scale. The old map is more complete than ours. Together, they show the essentials of good maps, details supported by a framework true to size and shape. Sighting by telescope from high places, the mappers have thrown big triangles across whole countries. But you cannot sight across an ocean. For a world map, we need some grasp of the entire Earth. As we roll along a straight road, our point of view changes, just as it did on Mr. Jefferson's lawn. Nearby buildings skim rapidly by, but the background skyscraper stands still in the frame of the car window. That simple experience will allow us to map the whole Earth by looking up into the sky. The stars in the sky are always background. No one will ever see a star cross in front of any house or a mountain or even the moon. The patterns of the stars, too, what we call the constellations, never shuffle about, no matter how we change our point of view. They remain the same in form over the centuries and around the world. Look at brilliant Orion. There are more bright stars in that field than anywhere else in the sky. And Orion is quite recognizable in this old drawing made 1,500 years ago on the other side of the world in China. The stars stay put. It is the foreground that changes. The hills, the trees, the buildings, even the distant horizon as we shift about on the Earth. That single old understanding that the remote stars are an unshifting backdrop is the key to mapping the Earth by the use of the sky. Watch Orion for a while. From this point, it will follow the same path in the sky every day of the year. But watching star paths change as we move about on the Earth is the way we can map this planet. You'll make your right, this is it.
All right.
Ah, that's what I was looking for. There's the water tower, officially Bassett, Nebraska. We traveled here to the heart of the continent to find the road we need. Here in Bassett, we are at the north end of Route 183. We turn to face south and at once park parallel to the road. Down this road, we hope to measure the size of the whole round Earth. It will take a day's drive with a big portable instrument for sighting on a star. Look, straight ahead, Phyllis. It's right on the road. It's all the way to Kansas.
And the sky, just big.
Yeah, and I don't think anybody passes this little piece of road at all.
Not
Let's
many.
try it here, okay?
Okay.
We named the van Eratosthenes, after the Greek mathematician and astronomer who first proposed a way to measure the Earth 2,000 years ago. There's something audacious about human beings about 6 feet high or so, measuring the form and the size of the planet we live on. It's something I've always wanted to do directly, not to depend upon the airplane pilots and the atlases who know very well how to do it. And we can do it, right from here, with our principal instrument being this fine yellow rental truck. The van is aligned with the highway. Both lie north and south along the axis of the turning sky. Tomorrow, US 183 will take us south through Kansas. Here's the plumb bob, Phyllis. Let's swing it and mark it if we can. We needed to relate our van to the center of the Earth. I'll hold the line for you. Once more, gravity did that job. Okay, down, down. Great. Knows which way to go. To measure the Earth, we sighted the same star from 2 positions. One here in Bassett, one the next night down in Kansas. The taped mark checks the level of the van at both places. That does it.
Here we go.
We had only a few stars to choose from this chilly May night. Our star was bright Antares. It rises soon after dark to cross south, well past midnight. Sky photographer Dennis DeChico records the smooth movement of Antares in photographs taken here every 15 minutes. With time collapsed, we watch the sky darken. Bassett glows a couple of miles south of us. We waited for Antares to rise at the left of the frame toward the east. First, we saw the planet Saturn. A little below it is our star. Antares at its highest arcs south. Look now, it is right above the vertical wall of the van. If I'm looking down that wall to mark that point, I will always see the star, any star I choose, at the same part of its arc. I can mark that position, which I will do with tape along the flat wall of the van. We do that here. We'll do that at the end of our journey in the south and see if there's any difference between the 2 results. Okay, Phyllis, try the ladder. I look between a pair of pegs fastened to the van wall. Come a little forward. Phyllis moves a wooden rod along the top of the van until it just blocks my glimpse of far Antares. Back now, back just a small amount. Slowly, slowly. All right, I think that's about what I can do. It's a hard thing to see. Shall we mark it? Okay.
Straight?
Looks quite straight.
Right there?
Yep, just below the peg.
All
Good.
right.
The tape marks the line of sight to the star from the leveled van in Bassett. Want to take your picture, Dennis? It looks fine. The plumb bob tied our observation to the center of the Earth. From Bassett, we marked the line to Antares at its highest. Antares is so far away that it is in the same direction from any place on Earth. The angle on the van shows how far we have come around the curve of the Earth. It always matches the angle drawn at the center. Next morning, we start south. US 183 runs straight north and south with hardly a curve for 400 miles. Extended far enough would link the North and South poles. We keep an accurate record of the miles, and we estimate the small loss to curves and detours. Bend with the Calamus River in the morning. All day long, there was only one more curve. Midnight in Coldwater, Kansas. We point the van wall due south to catch Antares once more. The trip mileage and our allowances for curves and a detour put us 370 miles south of Bassett.
Okay, come on back. Keep coming.
We level the van again.
Whoa, whoa, that's good. That's good.
Okay.
It comes to the proper edge. I think it's good.
Okay, let's check it one more way. Watch the shadow.
Aha.
How's it look now?
Oh, nice.
Does it
comes
touch?
in and touches. Okay, no, you're coming too close to me. Go back, back. I've got it in the sight. It's awfully close. Star, rod, yep, they're in line. Okay, I'll look along here while you do it. And then Janet, right below the peg. Okay. The two lines marked on the van show how much higher Antares arced over Kansas. That difference is direct evidence that our journey on the flat plains carried us partway around a curved Earth. It's a mark. We got it. Now we are able to reckon the size of the big Earth. We've transferred the arc between the lines on the van to the paper circle. The circle stands for the path around the Earth. It differs only in size.
1,
2,
2, 3.
Each step of the divider amounts to 370 miles of highway.
7,
8,
69,
0,
71, and 3/4.
We had 370 miles per step. And how many steps?
71.8.
26,600 miles. We measured the Earth in the yellow van with a result close to what the books give, maybe 5% large. In a day's drive and 2 nights of star watching, Phyllis and I have circled the whole planet, part of the way on the road, but more of the distance in the mind. The path of Antares in the sky let us judge our motion south. Here's the Arc of Antares we saw from Bassett. And in cold water, it arced higher. If we had kept on traveling southward, Antares would have risen higher and higher. But when we move east or west, the stars do not change. Every place that shares the same stars lies on the same line of latitude around the Earth. This handsome small object was made by a craftsman, Nicholas Lane, in London, about 1780. It is, of course, a small globe of the Earth, as they saw it then. Pretty good map. Every young person in a good family had to own and study such a globe, learn the parts of the globe. We do that today. Our libraries and our schools, quite traditionally, have globes of the Earth. But what they did, that we have somewhat forgotten, the case of this globe is not merely a black case. It is another globe, the globe of the sky, into which the Earth so intimately fits. They knew that relationship, and we tend to forget it, though map-making remains based upon it. I don't think we're in Kansas anymore, but just where we are, I don't propose to say for a while until we place ourselves on the map of the Earth by using the starry globe of the sky.
Oh. Tom, would you give me a hand with the clock?
Yeah.
We have brought along a surveyor's transit, a telescope, and a clock.
Let's see, I believe.
Surveyor General Andrew Ellicott came here by order of President George Washington. He carried 3 instruments like ours to map this very hill.
Weight's about 100 pounds.
Okay. Here we go. All right.
Mapping the frontier was something like a grandfather's clock. Well, in 1797, Andrew Ellicott did bring a fine pendulum clock he himself had made.
All right. I think I can probably lift this right up and out.
Our similar clock was also brought by the man who made it, Jim Moss from Massachusetts.
I like the way they made these things in the old days. They threaded them all together so that you can take them apart and put them together very easily for transportation, sure.
Okay. There we go. All right. All ready to go.
I've used a K&E, but I'm more used to a Gurley. All right.
Tom Hendley is an experienced professional surveyor. He sets up the surveyor's transit. It is a small telescope fitted with neatly graduated circles.
Uh-huh, 360 degrees.
Mm-hmm, all the way. And I go to the other two.
First, the transit must be leveled.
Right.
Okay.
All right, I think we're just about there.
So effectively now this whole entire plane of the transit is completely level.
Yeah.
Okay.
That's right.
Uh-huh.
Level with the world. All right. Now give me some light in the
Right.
crosshairs.
Okay.
A little bit more.
Like old Ellicott, we map under the night sky.
Now they're lit. Hold it just like that. Now I can see that.
Okay.
Let me get clear.
The scope has fine crosshairs that allow accurate pointing, provided you can see them by a little bit of light leaking in from a flashlight.
All right, I've got
Okay.
it.
The little telescope with its divided circles measured the star path much more accurately than looking along the van wall.
All right.
Got it?
Using a star whose place in the sky is known, We have put ourselves on one definite circle of latitude on Earth. But where along that worldwide circle are we? The clock can tell. But no pendulum clock can keep time in transit. It has to be reset at every new location. How to set the time? We will set our clock to local time by the stars, just as Ellicott did. Star time, not the same as standard time, is the astronomer's time. To read star time, we simply note which star is at its highest. Orion lies between the 5 and 6 hour marks. It takes 24 hours for the whole sky to turn overhead. Imagine watching the Earth from outside the turning sky. Our point of view is above the North Pole. The whole sky clock pivots around that axis. Every star has its own place on that dial, so every star marks a definite time. Tonight we use a bright star named Spica. If anywhere in the world you see Spica at its highest point in its arc, just at the top, then you know that the star time is 13 hours and 24 minutes. That's how we will set our clock to local star time. It is not easy to know the moment a star is on the topmost part of its arc, because its path is so flat there.
Okay,
Okay,
I think
you're
we're ready
starting
to go
your
now.
clock.
We'll level.
Pretty level? Okay, I guess we're about ready.
Okay.
See what you We'll use an old trick, just as Mr. Ellicott did 2 centuries back.
All right. Okay, I've got it in the field of view.
It's in the
Get this-
field?
3, 2, 1, mark.
Got it.
Okay. We time the star in the transit twice. First, as it moves up past the crosshair, and then as it passes down again. The peak is in between.
You ready, Jim?
Yeah. Will you
She's
give
coming
me a-
down.
Okay. Give me a countdown if you would.
All right, I will. It'll be just a little bit more.
Okay.
Okay, it's getting close. Get ready?
Ready?
All right. Mark.
Got it. All right. Okay.
Okay, so
All right.
that's the end.
All right.
Now we can find our local star time. By splitting the difference in time, we can set the clock by Spica even after the star has actually crossed the top of its path. Naturally, we have to keep track and allow for the time it takes to do all this. I'll give you the time by Spica. We can set the clock.
Okay.
Okay?
Uh-huh.
Okay, Jim, if we set it smoothly ahead to 1:44, I think we'll be quite close to the right star time.
Okay.
A few seconds won't matter.
2, 3.
All right,
4.
it's going now. Right, the hands are moving?
They are.
All right, we are set to local star time. Now we know when we are, but still not where. Spica comes by to mark the time, but it does that once a day wherever you can see it. To find our place on the map, we need to know current star time at some other well-mapped place. Then the difference in time tells how far apart the 2 places lie around that dial. I am going to call the observatory in Paris.
Allô?
Phil Morrison here. Suzanne, please tell me your star time in Paris.
Bien. 5, 4, 3, 2, 1, top. It was 20 hours, 2 minutes when I've given the top.
When Suzanne de Barba called top, our clock read 13 hours, 55 minutes. We are a little more than 6 hours earlier or westward from Paris. That is about a quarter of the whole circle and marks our longitude. We have to be where our latitude and longitude circles cross. Natchez, Mississippi. We happily report its address as we found it. Latitude 31 degrees, 32 minutes north. Longitude 91 degrees, 29 minutes west. Andrew Ellicott came down the Mississippi and here to Natchez because that was the frontier of the United States. The fledgling country sent Mr. Ellicott, its best-known surveyor, to mark its frontiers, its boundaries. That was why he did such a good job of measuring the position of Natchez City. But how could he do it? We could do it because we were able to make a telephone call to a distant friend and learn what star time was in a remote spot. He had no telegraph, no telephone, no radio, not even a spring-wound clock reliable enough that could be transported to bring him the time that was current in some other city. But there was a way. It was in this instrument, a telescope. 200 years before his time, Galileo had shown that if you look through a telescope, good enough, almost anywhere, almost any time, you can see a great clock in the sky. The clock is the distant planet Jupiter. Its hands are the little star-like moons that dance around the planet. Here are their motions, filmed in sped-up time on one single night. 3 of them come and go in front of or behind the bright disk of Jupiter. Such events can be timed to a minute or better. To use this clock, we need its schedule, a prediction of the time when a moon event would be seen. Here in the Observatory of Paris, new 300 years ago, they first of all calibrated and made useful the clock in the sky. Galileo knew the moons of Jupiter could make a clock, but he could never carry the matter through practically. The brilliant staff of this new observatory could do so long after Galileo's death, and founded upon their measurements of the moons the first scientific map of the world. The astronomer Jean-Dominique Cassini was brought to Paris to work out the schedule of the moons of Jupiter.
He arrived on the 4th of April, 1669. And he went at the Paris Observatory first in September 1671. These are the ephemeridus, which have been published in 1668.
Suzanne de Barba is senior astronomer and historian at the Paris Observatory. And now we're looking for the tables. And here we have, oh, very nice, the tables and the drawings that he made of the satellites of Jupiter day by day. So here is February, I see, of 1668. And here is drawn Jupiter.
Yes.
And here are the moons with numbers. And then a dot for where he says the satellites will be. And here he gives you some times of eclipses and so on.
And there you have satellite number 4 on right side of Jupiter, crossing Jupiter, and you see it on the other side, crossing a new time Jupiter.
Yes.
Which is there.
Yes, it's nice. And so this is the dance. And that gives some idea how we could calculate the forecast. Could we look at the late tables they made in Paris?
Yes. Est-ce qu'on peut avoir les tables de 1693?
Cassini could now predict very well the time of eclipses of the little moons as seen in Paris. Ah, this is the schedule of the clock in the sky. Here are the numerical tables for the positions of the satellites of Jupiter.
Yes, and you have the hour, the minute, and the second.
And with these and a fair telescope, not too big,
Not too big indeed.
a trained person could find the time in Paris if he watches the satellite of Jupiter. We could have used our telescope to find our location at Natchez. That is how Andrew Ellicott mapped his hill. The stars he watched provided local star time. And the disappearance of one or another of Jupiter's moons gave him the time in Paris. Cassini's tables had made Paris time available everywhere through the clock in the sky.
One of the very first applications was the mapping of France. And you will see the map of France.
Oh, yes.
And when they have used the table from Cassini, they went to the coast and they observed the eclipses of the moons of Jupiter in Dunkerque, Calais, Dieppe, Le Havre, Caen, Cherbourg, the Mont-Saint-Michel, Saint-Malo, and for instance in Brest.
In Brest, it's 50 miles different.
Yes.
Inward. France was bigger before this
Yes.
map. Before Cassini, they mapped France the best they could, without any means of finding an east-west position from the stars. In the 1670s, the observatory sent the astronomers out to map important towns all over the country. The result? The coast of France shrank in towards Paris by as much as 60 miles.
And when Louis XIV has seen the map, he says that I've paid my academician and they have reduced my kingdom.
Which does seem unfair, but I'm sure he was only joking because it's a brilliant map, probably the first accurate map made anywhere, quite accurate, a few miles in error compared to present day. Cassini's next step was more ambitious. The observatory sent travelers from France to map wherever they went. It was here, in this circular tower room of the Paris Observatory, that Cassini presented his circular map of the world. He put the North Pole in the center, and Paris fell along this line about there, and another place, say Mexico City, 10 or 12 feet out there. A circular framework of latitude and longitude was laid out right on the floor. Lisbon, London, Constantinople, Cape Verde, Quebec, Peking were all there. Over the years, 40 cities and more were entered properly. Last of all, they drew the coastlines, still little known in the far places. World maps had been undertaken for more than 2,000 years, but they could only be rather crude. This was the first map ever based on a consistent framework of measured geographical locations. At first, it was drawn in ink on the original stone floor, but that soon wore away. Happily, its final form is preserved in print. This marker pins the map of the world to the Earth itself. When they first made a modern map of the world in the Paris Observatory long ago, they had a few dozen such markers, points where a trained observer had carefully measured the address of some city or landmark around the world. Nowadays, we can count them by the hundreds of thousands. This is one of a set that outlines the edge of the harbor of San Francisco. Whenever you want to make a good map that will fit into the map of the world, you better begin with such a well-known control point.
What's the strip and roll number at the top?
Most maps today are made from long strips of photographs taken from the air.
Okay, looks like we need an extra point on strip 10.
A photograph is a fine start, but it is no map. The plane tilts and banks and drifts as it flies. The image is a little distorted. A hand can tilt too, until the shadow is adjusted to fit the drawn outline that maps its true shape. Here is truth on the ground for the aerial mapmaker. He knows that where these three roads come together is a marker that is pinned to the world map. The photo, with the pinned down points marked on it, is projected onto a drafting table. The correct framework is laid out there too. The operator tilts the table, seeking the best match between the projected air photos and the few known points that mark fixed locations. Now the map drawing is prepared step by step for eventual printing. Final details are entered by a skilled hand. Roads are never mapped at their real width, but are exaggerated. Every mapper finds symbols for some of the features. A finished map suggests certainty, but even the most artful representations of Earth are no more reliable than the few points that pin them down. Up till now, we have thought of mapping the world as mainly a visual matter, a sight line, some version of this. Sometimes through laying out a tape, measuring cloth. But more and more, the world is being mapped by a method that you can, so to speak, do with your eyes closed. Suppose we knew a runner of very steady performance who ran always in a straight line. By timing his run, we could know how far he had come and reduce the mapping of the world to time. There is such a runner. It is sound in air. Let's try it out and see how it works. Our runner is the sharp note of a trap drum. Each single tap sounds clearly from the far goal, but it takes time to arrive. There is a quicker way to hear the drum beat, through a walkie-talkie. Okay, I think now we'll start with the real thing. So maybe a succession of good head hits, and we'll listen carefully to the double sound.
Okay.
Now I hear the drum beat first over the radio. The direct sound is delayed.
How did that sound?
That was great. I could hear the delay every time. I heard every single drum beat twice. Once, almost without delay, by radio on the walkie-talkie, and a second time at the speed of sound through the air. Once I learn how to measure that time delay, I can associate a time with a distance and use time to map the world. When split-second timing replaces sight lines, we can even map where we cannot see. We join some sport fishermen off the coast of Massachusetts who time electronic drum beats to find the way back to an old shipwreck. The wreck is just south of the shallows at Hedge Fence Shoal.
We're on the shoal right now, 20, 25 feet. Should be coming off.
Yeah, it looks like some rips up ahead of us, Arnie. I think we're right about here. Look at this. The top of the shoal is about 9 feet. There's a severe drop-off here at 56 feet. That must be where the rip is. And right here is our wreck symbol. Is that the one we're looking for?
That's the one.
Beneath the boat, a kind of loudspeaker sends out a regular series of ultrasonic drum beats. They echo from the bottom of the sea. This instrument times the round trip of each pulse and plots out the wavy profile of the bottom as the ship sails along.
Where are we now?
I think we're right about here on the chart, Arnie.
Okay, that looks good. The wreck should be right in this vicinity. Joe, keep a sharp lookout. We're in the vicinity of the wreck now.
Currents swirl about the wreck. It is worth watching for some sign of them. The depth recorder shows the mounds of sand that those currents have deposited around the wreck.
What will indicate the wreck is a peak, is that correct?
Right, should jump up quick. Sharp peak. Quite different from the natural bottom.
Right.
Okay, Arnie! We got some swirls right down there! We got some swirls! Bring it around!
Look at that, wow. Look at it coming up. Look at that sharp spike.
Look how it contrasts. It comes up sharp, up to about 20 feet, from about 60 feet. You get a peak like that, I think there's very little question. It's not a sand wave, that's a wreck.
The deep oceans have been mapped for a century. By now, 1 million reliable soundings are charted worldwide. To fix those depths on the map, the ship must be located as it sails. That, too, is nowadays done by timing, but not with sound at all, by radio.
Space Vehicle 8 ought to be over on the east side. Yeah, looks good. Let's put up the antenna receiver and get ready.
The sky still offers the best way to map the Earth. But now we use man-made stars.
Okay.
A parade of special satellites 10,000 miles high.
Okay, let's get a check just to see that we're in the ballpark of the time.
At the tone 0 hours, 58 Universal Time.
Okay. Okay, the program is being loaded now that will determine our position with respect to the center of the Earth using the 4 satellites that are above the horizon now as a frame of reference.
Operators, Phil and Pete.
We have come back to Ellicott's Hill in Natchez to test out these up-to-date techniques.
Okay, now where are we?
Let's give it Mr. Ellicott's numbers. You want the latitude first?
Latitude. Yes.
Okay.
Minutes.
He says 31 degrees, 34 minutes nearly.
34. Longitude?
Longitude, 91 degrees, 29 minutes west from Greenwich. Mr. Ellicott's coordinates for this hill will give the computer program the hint it needs to get started.
Make that Natchez, too.
After a little wait, we will have signals from several passing satellites.
Ready to go?
Suppose the path in space of each GPS satellite is known at all times. The radio pulses each bird sends out give its position and the exact time. We time just when the signal arrives and carefully note the brief delay. We are somewhere on a circle whose size is reckoned by the known distance from the satellite. A second satellite, a second drumbeat, a second circle. We are at one of two possible intersections. A third satellite puts us right on the global map. A fourth allows checking. Every microsecond of time means 1,000 feet in position.
Summary, there's 4 satellites were used during this run. How many times we looked at each one?
Natchez, 31 degrees, 33 minutes, 44.44 seconds, north latitude, and the longitude with the same precision. Well, there it is. We began Mr. Ellicott's coordinates, and now we have numbers that are, I suppose it's fair to say, hundreds of times better than he was able to get. Of course, it's 200 years, something should have improved. Andrew Ellicott's painstaking work was excellent. But before electronics, precise time was hard to find. Half a minute of uncertainty in timing put his location off by 8 miles. Today's amazing electronic timing locates us within 50 or 100 feet in any direction. This is the future of mapping. Agreed now that maps are of the highest importance. They're important to the mind. We always want to know where we are. I believe they mean even more than that. They are essential to a grasp of science. For in science, very often, we build visual representations, maps, out of something that does not dwell at all in space with us. Listen to these musicians. We will build an example of what I mean out of their music. It will be mapped in an imaginary space, but not in fantasy. A map as real and faithful to the music as a good highway map represents the roads of the state. Now we can see the building up of the map of the music. We work from an earlier recording of the same tune. It's not hard to pick out at least one of the rules of this mapping. Loud sounds are peaks. Valleys are soft. Less easy to see, the music is also sorted according to pitch, with the treble over here always, and the low notes toward the bass over there. The computer samples the music for a short time and draws a profile, and repeats in a fraction of a second, over and over again. The many profiles are arranged in order and made into a movie that goes in time with the real music. Let us watch it again. The diverting landscape of the Tabla Mountains was not something in the music itself. Yet, given the structure, the map represented the music quite faithfully. Ideas commonly dwell in space. We often speak of one idea as being behind another, of two notions being close, of two statements requiring a connection from some idea in between. Yes, theories in all of science are like maps, though sometimes they live in strange spaces not in 3D or 4D with us. Sometimes they shift rapidly, as once the mapped coast of Sun King's France appeared to dwindle. Sometimes they endure for thousands of years, like our recognition that the Earth is really a round ball. We have seen in the Music Mountains a visual representation of something that never existed in space, which was simple and clear. But we cannot always expect our theories to lead to simple pictures of what was never visual in the first place, although we always try.
Next, focus in on the years following World War II, when the 7 major oil companies wielded their power around the world. What part did oil play in the domination of global commerce to the stability of governments? Investigate the 7 Sisters on oil, next on KCET. Timeless story of love and truth is brought to life by an unforgettable cast. Lillian Gish, Sam Art Williams, Geraldine Page, Butterfly McQueen, and Patrick Day star in The Adventures of Huckleberry Finn. Then at 10, it's a factual account of the Salem witch trials, a time in America when truth was corrupted and innocent people were made to suffer.
The Lord Christ knows how many devils there are in his church and who they are.
Vanessa Redgrave stars in 3 Sovereigns for Sarah. 2 great dramas back-to-back on American Playhouse, Monday beginning at 9.